Hello, welcome back to this series of videos about the Satoshi's white paper. And now, where have we left last time? To reclaiming disk space. So here we go. Reclaiming disk space in this context is referred to, hey, we're storing the whole blockchain. We are expanding it each 10 minutes. It gets expanded and expanded. So what about talking about storage? Where do we store all this stuff? And the direct response in this paper is you don't store it all. You just store the last transaction, the last one, plus the hash of this transaction block. Sorry, this is not just a transaction. This is a transaction block, which we need to hash, save the hash. We need the hash of the previous block. And we have this linked list, basically, where each hash will also have the reference to the last hash, to the previous one. Therefore, what we have is that we will hash all these references together, and we will obtain another hash, which needs only its specular hash in the root and the tree structure we have here. We proceed towards the root, where we have the last hash, which will include references to all the hashes we mentioned. And what happens is that with this hash here, we will put just previous hash reference, which is this one in this case, if I'm not wrong. Yeah, if I'm not lost in the meaning of these nodes and edges. And then we have a nonce, which is the randomization we need to introduce to be compliant with the rules in the whole network. Because when we will complete the hash of this block, each time we will try and see, does the number of zeros indicated here coincide with the result I obtained? And if not, you continue and continue, hash and hash again this block, varying the nonce, and then eventually you can resolve it and obtain the reward. In the moment in which you receive a new block hashed here, it means that somebody resolved the next block. Therefore, all your structure will need to take out this hash here and build everything again from the next block. Therefore, if you just want to check if new transactions are good to be accepted, you just need these few informations, which require really a low volume. It's a block header with no transaction will be about 80 bytes. If we suppose blocks are generated every 10 minutes, which is what happens in reality nowadays, 80 bytes per 624 365 means, because they will be I don't know why, there will be 6 blocks each hour and 365 days each year. Per year we will spend 4.2 megas. That will allow us to be sure that the transaction we received respects the consensus and the blockchain history. Of course, there may be, I can imagine some cases in which this affirmation will not be necessarily true. I can imagine them, but I cannot encode them. Not sure if this is just an idea, which maybe it's just a broken idea in the start, but maybe there will be something which pruned nodes, which are the nodes that will store only the headers without transactions. So what happens to these nodes? They will be able to check something, a partial truth, and I'm not sure about why, but I've heard some argumentation about why being just this type of node, it's useful until a certain point. Then we have, let me see one thing, if everything is working here. Yes, it looks like it's pretty smooth. So we have the next chapter, which we'll discuss in this video. And then we have chapter 9, chapter 10, and 11, and they look quite big. Therefore, let's start and see if we can finish in this video chapter 8. So I started this series of videos with a literary approach. A literary approach in the sense that I start from analyzing the text structure and also the use of images, but yeah. So we have two main paragraphs in this chapter. Both paragraphs are quite big. Watching at the other paragraphs dimensions, we found some bigger, but yeah, for example, in this case, they're all smaller. Yeah, they're huge paragraphs. In this case, in this chapter, which is one of the most, I would say, the most important, looking at the innovation that this paper brings. Yeah, chapter 4, and it has huge paragraphs. Also in chapter 2, yeah, well, maybe it's not that important, but I was curious. So the first, between these paragraphs, we have another representation of a series of block headers which only have the Merkle root, and how we will see we can do something with this. So it's the proposition of this type of pruned block. It's called the pruned block, this. So a series of pruned block, what is just a series of block headers. We calculated here how much they will occupy them per year, so they are attractive for, let's imagine, simple devices, simplified payment verification. So simple devices, as I was mentioning, when you act in this way on your capacity of memorization, you will reduce, of course, the things you can achieve as a node, but in exchange, the node can, this type of nodes can be run on machines which do not have a lot of memory, and maybe in some cases also machines with low computational power. You can imagine like point of sale, you know, those that normally people will use to allow you to pay by card. Those are really simple devices which will do something that cannot go wrong. You cannot accept that a guy comes to your shop, they want to buy, and they cannot because that machine doesn't work. So those machines are normally simple, tiny, reliable, and what you want from machines like those is to operate in a good manner all the time. So reducing the memory it has to manage, of course, reduces a lot the convenience that can happen to that machine. So from here we have this idea of simplified payment verification. It is possible to verify payments without running a full network node. And in this paper, therefore, we have this distinction between a node which runs all the stack, so memorizes everything and participates to the network in a fully way, running all the services of a node. On the other hand, you can instead imagine a user that only needs to keep a copy of the block headers of the longest proof of work chain. So this is a possibility which then he can get by querying network nodes until he's convinced he has the longest chain. And obtain the Merkle branch linking the transaction to the block. It's time-stamped in. He can check the transaction for himself, but by linking it to a place in the chain, he can see that a network node has accepted it, and blocks added after it further confirm the network has accepted it. So this is what a simplified payment verification is able to perform. As such, the verification is reliable as long as honest nodes control the network, but it's more vulnerable if network is overpowered by an attacker. So this is, for example, one thing that you lose when you simplify your node. You are with that node, you cannot run operations where you need a higher degree of trust in the system. So while network nodes can verify transactions for themselves, the simplified method can be fooled by an attacker's fabricated transactions for as long as the attacker can continue to overpower the network. So one strategy to protect against this will be to accept alerts from the network nodes when they detect an invalid block. So prompting the user software to download the full block and alert the transaction to confirm the consistency. Business that receive frequent payments will probably still want to run their own nodes for more independent security and quicker verification. So it says you are losing so much in security that in the end, probably you will still want to run your own node for more independent security and quicker verification. So basically it's saying you take the risk. You cannot expect from this system to take care of your interest. This system will protect the common interest, will protect the integrity of itself, will protect the capacity to continue working, so the availability of this service. And everybody's working toward a collective goal which empowers the responsible individuals. So individuals are empowered by this technology, but not fully protected, not fully responsibilized, not fully the responsibility. It's not taking all the bargain from you. You will still need to work, paying attention to what you download from when, from where you download information and who is the people running those nodes. The difference with previous technologies is that now you can run verifications by yourself. You can run them and they are programmable. This is an important detail. The possibility to know how to program and the possibility to actually program something to check for your interest is the most powerful idea in this system. It's just this system is just allowing everybody to exploit that possibility if they want, of course, if they know how and if they want. Therefore, it still requires a lot of competence. You still need to understand that yes, in some cases you can just spend less resources and take the risk of using a simplified payment verification. But with this one, you are basically getting back to a system where someone is telling you what is the current situation of the ledger. The more people participate to the network, the more nodes everybody has from where to download information, to whom to talk, more nodes which will check if the protocol is run correctly. Because let's remember, what we understand in chapter 4 is that it's sufficient to run your node to be sure if the rules to which you adhere are being followed. Therefore, you can even change the rules, accepting that maybe you will not be followed by anybody, and you can choose to follow somebody, to follow the longest path. You can even decide to follow a shorter path, therefore going for a fork. Basically, this is a political instrument, and it allows us to create a transparent ledger where everybody has the possibility to check the context, being sure about the information they are reading. But at the same time, it's saying never be sure about what you're reading. Try always to understand that you need to run your node, you need to check things, you need to check the health of the network continuously. You have to understand that things are working. So this is a really at this stage, using this system, fully understanding it, not only is so complex, it also requires a lot of energy actually. Therefore, people who understands it now has this, if they really believe it's a good technology, inevitably, it's inevitable that who thinks that this is a good technology will act as an evangelist of this technology, because the key point of the technology is political. Therefore, this type of paper which proposes a solution to a political issue requires political thinking, economical, political, philosophical thinking. It's a really profound chapter, this one. It's a really profound statement, the one here. It's anticipating what people will try to do. They will try to simplify things, to reduce. Of course, the previous chapter allows for more users in the system, but with this statement, it's saying, okay, we have all these improvements to make things simpler when needed, but it's also saying that you will probably still want to run your own node for independent security and quicker verification. It's really interesting how this statement is making all these paragraphs until here, so the last 4 paragraphs, the last 2 chapters, it's making them like not something wrong, but something where you will need to be cautious. You will need to move slowly. Okay, therefore we spent 20 minutes on that chapter. Maybe we can pass to chapter 9, combining and splitting value. Although it will be possible to handle coins individually, it will be unwieldy to make a separate transaction for every cent in a transfer. To allow value to be split and combined, transactions can contain multiple inputs and outputs. Normally, there will be either a single input from a larger previous transaction or multiple inputs combining smaller amounts, and at most 2 outputs, one for the payment and one returning the change, if any, back to the sender. So here we are playing a lot. In this tiny paragraph, we have a lot. Then we have this paragraph resumed in this schema here, and then we have, it should be noted that fan out, where a transaction depends on several transactions, and those transactions depend on many more, is not a problem here. There is never the need to extract a complete standalone copy of a transaction's history. So this sounds like magic. Okay, therefore, here I was saying that there's a lot, because although it will be possible, I need water, sorry, my mouth is drying. Okay, so I'm back. Although it will be possible to handle coins individually, it will be unwieldy to make a separate transaction for every cent in a transfer. To allow value to be split and combined, transactions contain multiple inputs and outputs. Normally, there will be either a single input from a larger previous transaction or multiple inputs combining smaller amounts, and at most 2 outputs, one for the payment and one returning the change, if any, back to the sender. So one interesting thing here is to ask, let's see if we can access this. I stay log out. How many? So I am looking for a little number. I mean, not a little number, a couple numbers which will give us a bit of context about this chapter. How many addresses are possible to be generated with the Bitcoin address creation framework. So we have a framework which is defined by the public key generation algorithm, the public key. Well, yeah, it's just the generation of the public key, the address format, the public key hashing. So these three things define, all the combinations. So all the private keys we can choose are this number here, 10 elevated to 77. Since each private key generates a unique public key, the public keys are the same. Therefore, a Bitcoin address, after applying the hash function and blah 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 to the public key, the final Bitcoin address is a 160-bit hash. This results in 2 elevated to 160 possible Bitcoin addresses. This is approximately 10 elevated to 48 possible addresses. So as the bot is also saying, this is an astronomically large number. So, okay, so this is a good example. In practical terms, this means that it is virtually impossible to run out of Bitcoin addresses, as the number of possible addresses with this system, which we can generate, is many orders of magnitude greater than the number of atoms in the observable universe. So before finishing the Bitcoin addresses, we will finish the atoms. No, I'm joking. We will finish them at the same time. What happens here is saying, imagine I'm paying you 2 cents. It will be unwieldy to make a separate transaction for every cent in a transfer. In my example, that will be two transfers, but imagine 1 cent, a bigger order of coins. That will be an issue. We will have too many transactions, and that will be crazy. And why we are considering this is because we are basically considering an electronic cash system. Therefore, we are thinking to these objects, which are the tokens that I mentioned sometimes, saying that normally we think about banks, and banks are account systems. They are not cash systems. Cash is a fungible token with other characteristics which I don't remember in this moment. And by fungible token, you mean that you cannot distinguish one token from the other. They are all fungible at the same way, fungible as the same coin. The €1 coin, or I don't know, another coin which you can imagine. Therefore, we have also the 1 cent coin. What happens here is saying when you transfer some coins to somebody, you are transferring coin by coin to them, and in this system it will be crazy to think about that. We will have too many transactions to report. Therefore, to allow value to be split and combined, so as in the cash system we have like different aggregation of the currency value, also here we need something, and transactions contain multiple input and outputs. Therefore, in a transaction you will have many ins and many outs, like when you go and you pay with 2 pieces of €50, and they will give you back So these two pieces of 50 euros will be combined in at least one output, which in case you give the guy the correct number of the correct amount, they will just take that money and that's all. You will have just one out signal. What happens if they have to give you change? They will give you back in another output object, output item. They will define a change given back to you. And what happens if you, for example, you pay you 50 and a friend of you put another 50, and they will have to give you, to get those 100 and give you $3 each. You see, you will have many outs here. And all of this is coordinated, this is combining splitting value. And normally there will be either a single input from a larger previous transaction or multiple inputs combining smaller amounts, and at most two outputs, one for the payment and one returning the change, if any, blah blah blah. So here with this statement we are saying we work an UTXO. So UTXOs in short, BTC UTXO in short. So UTXO is unspent transactions, unspent transaction output. So an unspent coin. Remember that when you create a transaction, you write that transaction, so this guy here, the owner one guy, he needs to pay to this guy. So he will say, okay, I give him $50, and they will do some operations on this declaration. They will create a hash, and the hash will be created this hash will be signed by this guy with his private key. Therefore this guy will go backwards, so they will be able to verify. So I will put this arrow backwards from the owner's one signature to the owner's one public key, because the public key allows the verification of the signature made with the private key. So here we have how public key and private key go together. But what happens in this network is that you never show your public key. Or well, maybe yes, I'm not sure if in the transactions you actually put your public key. I think not. And I remember that well, yeah, of course there will be the public key, but in another form. Sorry, I was saying it right, that public key doesn't appear directly, because what happens, and this is why I got back here, is that here we read public key is useful to verify the signature, but in chapter 9, as we can observe, basically this transaction here uses inputs which have not been spent yet. Okay, so a guy that in a transaction puts his public key saying this public key is sending to you this input, is not happening in the form that this guy really puts his public key, the one obtained from the private key. He will put his address. Okay, and one thing that happens is that here the guy said it will be unwise to make a separate transaction for every cent in a transfer, but we will, what if we create a transaction for each coin we have? Okay, so what I say is that you never put two of your inputs in one transaction unless it's, I don't know, it's your last fund and you don't have other way. But what I'm saying is that the better thing is to use each time a different address, and the different addresses are generated from your public key with one direction hash. The hash will therefore allow you to obtain each time an address that it's not directly linkable to your public address. So I hope you followed me in this. It was rough, but what I was saying is that when you send to somebody an unspent output, each time you can use a different address. Each time this address will not be directly linkable to your public address. Therefore, there will exist many transactions which will only have this public address used once, and instead of creating a transaction each time you want to move a cent, you will create a new transaction each time you want to move an unspent output. Okay, therefore this unspent output, maybe it will be broken in two when it's bigger than what we needed to pay, but in the end what will happen is that coins get broken, they form other outputs, unspent outputs, and then they get aggregated when somebody needs to pay for something bigger than all their UTXO. Therefore, you have all these lines of tokens leaving and then being broken and then being aggregated again. And here it's interesting to remember that for each transaction, you never have the need, there is never the need to extract a complete standalone copy of a transaction history. Okay, because each unspent output will be will be checkable like this. Okay, so you will see that this output comes from another transaction, and just by looking at the headers of that transaction you can say, okay, this input for me works. Okay, this is the key point when saying that this is a cash system based on tokens, on coins, which of course, being digital, can be split and then recombined, but they work more like cash, like banknotes and coins. They do not work as accounts as banks do. So you never have you will not have your identity connected to a certain amount of coins. It's more like imagine a reality where the government cannot watch in your bank accounts at all, cannot even know how many bank accounts do you have, how the money are split between bank accounts. So the most similar way to look at things is this one, where you have multiple accounts, fragmented, and you cannot know all the payments that an account made unless you have the public key. When you have the public key in some way spilled out, because you voluntarily public your public key for some reason, which will not allow you anymore to generate a new not linkable address to your public key, because from your public key you can calculate all the possible addresses. So yeah, what happens in that case is that every unspent output you want to put in a transaction will have in it an address which is linkable to your public key. In the moment you publish your public key, and somebody then can track all the addresses you used, in that case they can track, aggregate all the transactions you've made. And yeah, this is a way they can reconstruct the history of one of your accounts, because then you have the possibility, of course, to have more public keys. Therefore you can choose to go public about one public key and not others. It has a lot of implications, this short chapter. Therefore, as it was a fat chapter, I will take a quick break, close here this video, and get back as soon as possible to continue with the rest of the chapters after a quick break. See you in the next video.